Hi friends, welcome to my channel. My name is Tepo and we are back. As I promised in the previous video that I will be back with some exercises based on the lesson that we had on our previous videos. So please subscribe to my channel to make sure you keep on receiving videos like this. So let's get to today's video. I have a question paper with me. It's a question extracted from a question paper. And then it says a 0.5 kg of gas at 310 kilopascal is compressed from a volume of 0.15 cubic meters and a temperature of 40 degrees Celsius to a pressure of 680 kilopascal according to the law PV exponent 1.35 is equals to C. The specific heat capacity at constant volume is 0.718 kilojoules per kg kelvins. Then the questions. Let's first make sure we have everything we need from this statement written in the simplest way possible. So they said our mass 0.5 kg of gas, 0.5 kg at pressure. Okay, first let's write this P1 T1 V1, then we have P2 T2 V2. They say at 310 kilopascal, at which that one is P1, 310 kilopascal is compressed from a volume of our V1 is equals to 0.15 meter cube, and a temperature of our temperature now is given in 40 degrees Celsius. And we remember what you said. You said in these formulas you do not use a temperature that is in degrees Celsius. So means must be done to convert this thing into we convert it into Kelvin. So when you convert it into Kelvins, we will just add plus 273, and then we get our answer that will be in kelvins, which is our kelvins will be 313 Kelvin. That's our temperature. Then we take this value, put it here, 313 kelvins, and then we continue to a pressure. Then now we have P2 to a pressure of 680 kilopascal. According to the law, this is the law by which our expansion or compression is performed. Now we have two methods which use this law, because in this case we were not told that this is R or it's M. So we do not know yet whether this is adiabatic or it's polytropic, but we will find out before we are done with this question. So they say that's the law. And then the specific heat capacity, let's erase this. The specific heat capacity under constant volume, it's equals to 0.718 kilojoules per kg kelvins. So that's everything that we have, and then we do not have this, and we do not have this. So let's see what are they looking for. Calculate question number 1. That's 2.1. Let's do this. 2.1. Calculate the gas characteristics constant in kilojoules per kg Kelvin. What we are looking for is our R. How do we go about calculating our R? We will use the formula MRT is equals to PV, and then we will use the information of the initial phase, since it's the one that we have the complete information of. We have P1, we have T1, we have V1. Then we will use those ones here, and then first solve make R the subject of the formula. It's really important that you do not skip steps in power machines and sites, because most of the steps that you will be skipping have marks. So make R the subject of the formula of P1 V1 divided by M T2 is equals to our P1 is 310 times our V1 is 0.15 divided by our M. Our M is 0.5, and then times our T1, which is 313, and then this will give us 0.297 kilojoules per kg Kelvin. And then we are done with our first question. Let's look at the second one. Calculate the final temperature. This is what they are looking for here. They are looking for T2. Like I said in the previous video, every time you are doing an exercise, make sure you have your table by your side. So I have mine mounted in the board here, to make sure that you do things quick and you do things as correctly as possible. So they are looking for T2. We go under between these two methods, because we know that either it's adiabatic or it's polytropic, but we don't know which one is it exactly. So we go to our tables here, and then we find a formula that we can use. So in this case, I have used T2 divided by T1. It equals to P. P2 divided by P1 exponent 1.35 minus 1 divided by 1.35. And then we are looking for T2. Let's make T2 the subject of the formula. T2 is equals to T1 in bracket P2 divided by P1 exponent 1.35 minus 1 divided by 1.35. So we substitute. Our T1 is 313, and then our P2 is 680 divided by our P1 is 310 exponent 1.35 minus 1 divided by 1.35, and then we calculate, get the value of our T2, and I got 383.698 kelvins. And then we go to our third question. They say calculate the final volume. So this is what they are looking for. They are looking for V2. That's our final volume. We come and we go again to the table, and then we look for a formula that we can use. In this case, I have used this one, our 2 point. Okay, let me write it here. I'm wondering if you can see there or not. Okay, let's write it 2.3. I have used P1 V1 is equals to exponent P1 V1 exponent 3.5 1.35 is equals to P2 V2 exponent 1.35, and then we are looking for V2. This is our V2. We have to make V2 the subject of the formula, and then we say V2 divided by V, or V2 divided by V1 exponent 1.35 is equals to P1. It's P1 divided by P2, and then we are looking for this. This must be done, so we make V2 the subject of the formula. V2 will be equals to V1 P2 exponent 1 divided by 1.35. Now we can substitute into our formula and get the value of V2. So this is our formula. It's from here. V2 is equals to V1. Our V1 were given as 0.15, and then in bracket P2, P1 is 310. Our P2 is 680, and then divided by exponent 1 divided by 1.35, and I got my answer as 0.0838 meter cubed. So that's our third question. We move to our fourth question. Let me erase this. Start on the clean slate. Our fourth question says, calculate the work done during compression. That's our 2.4, and then we are told to calculate the work done. So we go again in our table, look under work done, and then we have two formulas in which you will just have to choose one, and I have used this one, P1 V1 minus P2 V2 divided by 1.35 minus 1. I cannot write N or R here because we don't know yet which method is it. So I will just put it down as our 1.35. That's our work done, and then it's question 0.54. And then we substitute our P1. We have 310 times our V1 1.15 minus our P2 680. Our V2 we just calculated, the one that was here, as 0.08338. I hope that is the correct value. And then 1.35 minus 1, it's equals to, then our work done will be equals to negative 29.954 kilojoules. The minus sign now represents that the work wasn't done by the gas, it was done into the gas, sorry. Hence they are saying calculate the work done during compression. And then now we move to our 2.5. Our 2.5 says calculate the change in internal energy. We know internal energy is represented by change in U, and then we go under internal energy. Then we get that the formula to use is M times CV, change in T, T2 minus 1. And then we substitute our mass is equal to 0.5, and then our specific heat capacity under constant volume is equal to 0.718 times the change in T. Now we have T2 we calculated and we got 383.698 minus our T1313, and then we calculate and we get our change in internal energy as 0. At 25.381 kilojoules. And then we do question 5, question number 6, that says calculate the heat rejected during compression. So we go again, look under Q, heat rejected or heat received. Now it will be clear to us because we know, and between these two, polytropic and adiabatic, only one process has heat exchange, heat rejected or heat received, and that is polytropic. Since now they are telling us to calculate the heat rejected or the heat received. Sorry, they said the heat rejected. It will be clear to us now that the process that you are dealing with here is polytropic, because if it was adiabatic, then our Q will be 0. But let's calculate to make sure that what I am saying is correct. Let's erase this, and then we say the value of Q. Our Q is given by work done, and then I got this from my table, work done plus change in internal energy. Now we have calculated work done. I've just erased it, it was here, and we got a value that is like this, minus 29.954 plus a change in internal energy which is 25, which is 25.381. Then we get our answer as negative 4.573. That is the heat rejected, represented by this sign. The minus sign tells us that the heat was rejected. Then we have our last question that requires us to calculate the change in entropy. Change in entropy 2.7. This is 2.6. Change in internal energy. Yeah, that's Q, 2.6. Now we have our 2.7. They say calculate the change in entropy. We know entropy is represented by S2 minus S1. That's our change in entropy. And we have two formulas to calculate this change in entropy. So in this case, you will choose the one that will work best for you, considering the information given. So I have chose to go with this one. M in bracket CV ln P2 divided by P1 plus CP. Okay. Plus CP ln V2 divided by V1. And then if we look at this formula, we have everything now except for Cp. Remember, we do not have Cp. We have Cv, but we do not have Cp. So first, let's calculate Cp. We know Cp, we can get it using this formula, Cp minus Cv. Our R we calculated in the first question, and then we got a value. Okay, so first let's make this subject to the formula, then R plus Cv. Our R we got 0.297 plus our Cv at 0.718, and then we get our Cp as 1.015. Since this is the last question, let me erase this. And then we now substitute our m is 0.5. That's our m times our Cv. Okay, I did not do myself a favor by erasing these things, but let's just continue. Our Cv is equals to 0.718 ln P2. Our P2 is 680 divided by 310, and then plus our Cp. This is our Cp. Our Cp is 1.015 ln, and then our V's. V2 is 0.0838, and then our V2 is V1 is 0.15, and then we go ahead and calculate this change in S. We get a value negative 0.135 kilojoules per Kelvin. So that is the end of our first question. Nothing is difficult here. As long as you have your the table that I gave you by your side, everything will go according to plan. Then let's do our second question. I have another question here. Let's erase this one. Okay, the statement says a certain gas at a temperature of 26 degrees Celsius has a mass of 2.732 kg. This gas is compressed isothermally to 4000 kilopascal from 140 kilopascal. The gas constant for this gas is 0.3. Now let's try to present this information in a simpler way. We will have T, P, V, 111. We'll have T2, P2, and V2. Okay, they say a gas at a temperature of, our temperature is given at 20, is given in degrees Celsius, 26 degrees Celsius. Then we add 273 to make sure we have a temperature that is in Kelvin. Then we get 299 Kelvin. Yeah, I think that's the number that we get. But anyway, let's just continue. Our temperature here is 299 Kelvin, and then they say has a mass our m, so with our m here, is equals to 2.732 kg. This gas is compressed isothermally. They say our gas is compressed isothermally using this law. Then we know that isothermally T1 is equals to T2. That's constant temperature. To a gas, this is our P2. To a gas of 4,000 kilopascal. That is our final volume. From 140 kilopascal, that is our initial volume, kilopascal. Let me write a line. The gas constant for this gas is, our R is given by, it's 0.3 kilojoules per kg Kelvin. And then we erase this. Now we do not have V1, we do not have V2. Then let's look at the question. What really is it that we are looking for? First question. Calculate the volume before compression. The volume before compression, that is our V1. We can get V1 using this formula MRT1, because we are calculating V1 as equals to P1 V1. This is our 2.1. And then we make V1 the subject of the formula first. We have MRT divided by P1. Then we substitute our M is equals to 2.732 times 0.3, our gas constant, times the temperature, which is 299, all by pressure number 140. That's equals to 1.75 meter cube. That is our V1. And then our second question says, calculate the volume after compression. Now we are calculating for V2. Same method. V2 MRT 2 is equals to P2 V2. And then we want this, make it the subject of the formula. MRT2 by T by P2. And then we substitute. Our mass is 2.732. Yeah. And then our gas constant 0.3. Our temperature 299. And then our pressure is 4,000. Our answer for V2 is 0.0184 meter cube. And then we have our third question. They say calculate the work done in kilojoules. The work done in kilojoules. Work done. In this case, we are given two equations in our table under work done. We have the equation that involves us using the volumes that we just calculated. But since this information was originally given from the statement, I suggest we use the one that says P1, that says MRT ln P1 divided by P2. And then we substitute our M being 2.732 times our gas constant 0.3 times our T. Our T is 2 2.99. Lin P1 140, P2 4,000. And then we calculate, get an answer like this: negative 821.542 kilojoules. Then yeah, the minus sign represents that the gas, the work wasn't done by the gas, it was done into the gas. And then we look at our question number 4. Let's erase this one. 2.4. It says calculate the heat gained or lost in kilojoules. And then we go to our table under heat gain or heat lost. We know now that in constant temperature, heat, we get it by this formula: change in internal energy plus work done. And then we know that our work done is as a result of temperature decrease or temperature increase. But in this case, we are dealing with a constant temperature, which means we will have our change in temperature as 0, since there is no temperature difference, plus our work done, meaning that our Q is equals to work done. And since we have calculated work done already, we can just come and insert the number here and write it kilojoules. This is our Q. This is our Q. The minus sign represents that the heat was lost. As we can see, the temperature wasn't allowed to increase. So every heat that was supposed to increase this temperature was lost. And then we do our final question. We say calculate the change in entropy. Let's erase these. Now we have a formula in entropy like this: change in entropy is equals to our M times Cp ln T2 divided by T1 minus our gas constant ln P2 divided by P1. Now we know that this will give us 0, since we have the same temperature. T2 divided by T1 will give us 0. And we also know that ln 1 is equals to 0. Therefore, this part of the equation now, we let it go because it is equals to 0. So there is no use for us to rewrite it over and over again. We are left with an equation like this: M minus R ln P2 divided by P1. Now this we have, our M is 2.732, if I'm not mistaken. Yes. And then in bracket minus 0.3 times ln our P2 is 4,000 divided by 140. 4,000 divided by 140. And then we get our change in entropy as minus 2.748 kilojoules per kg. Yeah, per Kelvin. Yeah, per Kelvin. Yeah, this that will be the end of our exercises. I am sure we now see how to apply the information that we learned, that we got from our previous video. As long as you have the table by your side, nothing can go wrong. The table is very helpful, so it is very important that you have it always by your side. Yes, my name is Tepo, and this is the end of our video. Don't forget to like this video, share it with your friends, comment guys, and tell me what you think about today's lesson. Where do you think I can improve? Don't forget to share this video with other people so that they can get the same help that you've got. From me to you, see you next time.